Hi everyone, and welcome to another seminar of Physics Latam. Today we are very happy to have Professor Anton Kapustin with us. He's a theoretical physics at the California Institute of Technology, and he's interested in quantum field theory in general, with applications to particle physics and condensed matter theory. He has made several important contributions to duality and other aspects of quantum field theories. In recent years, he has focused more on mathematical structures and classification schemes or topological theories and symmetrically protected fields and topological phases. Please remember to raise your hand at any point if you have any question, and I will leave you with Professor Kapustin. Please go ahead.
Yeah, so thank you very much for inviting me to speak at this seminar. So maybe you could, before I start, I have some questions. So I'd like to, I'm not quite sure what to expect from the audience, especially it's an online seminar. So it's a mixture of math and physics people, if I understand correctly.
Yeah,
Is this correct?
that's correct. So
Yeah.
maybe people can write in the chat if they come from physics background or math background.
Okay. So yes, I'm going to talk about some subject which is really belongs to quantum statistical mechanics, and it's a fairly old subject. You'll see that this goes back to 1970s. Actually, even the roots of it even early in the 1960s, but didn't receive much attention until fairly recently. And it was approved. This was an important technical tool to understand structure of gapped phases of matter. And my interest in this started when I was thinking about topological field theory and how how topological field theories emerge from some lattice systems. And this is still a very um, um, difficult subject in the sense that we still don't know why um, some models that typically considered in the statistical mechanics have anything to do with topological field theory. So, and in this talk, in this lecture, I will not try to explain that. Um, there are, of course, results, but they're considered more special models. But I'm more interested in the general models, the general classes of models, and how one can argue that they're related to topological field theory. And at present, we are reduced more to um, constructing some invariants, some numerical or other invariants of topological phases of matter, and then or gap phases of matter, then verifying that the kind of invariants we get are the same kind of invariants that topological field theory predicts. So it's not really proving that topological field theory is there, but it seems like that you can prove, basically we're trying to argue that the same results that you can get from topological field theory you can also obtain more directly from quantum statistical mechanics. But it's going to think it also as evidence that field theory is relevant, topological field theory is relevant for condensed matter physics. Okay. So now the subject of quantum statistical mechanics, unlike field theory, which is very still on shaky grounds, is in some sense it is very simple because it's about okay, so it's a pretty large subject, but for the purpose of this talk, I'm going to focus on lattice systems, and lattice systems is basically just infinite arrays of qubits in space. So what's a qubit? Well, just the simplest non-trivial quantum system. It's Hilbert space. It just has dimension 2. And system of n qubits has a larger Hilbert space, still finite dimensional. So just 2 to the power n dimensional. Now, and then we're interested in general, well, more interested in infinite arrays of qubits for reasons I explain later. But for now, just look at finite ones. So a pure state of a system of qubits, even it's finite, is just a vector in a Hilbert space. By the way, interestingly, if you look at the definition of a pure state from purely mathematically, then there may be, for infinite dimensional Hilbert space, there may be pure state which are not of this form, but for now, we're just looking at finite ones. and then that's really true. And if your Hilbert space is made of qubits, then the simplest ones are just products of like factorized states, where just a tensor product of a bunch of vectors, one in each qubit vector states of space. So they're called unentangled. So this system of qubits important both in quantum information and quantum matter. And in quantum information, we're interested in manipulating these qubits using some called gates, some elementary operations on qubits. And we would like to know, given a supply of gates, like some particular gates we have in our toolkit, what sort of states can we prepare, and how difficult it is to prepare a given state. For example, how long it takes. In quantum matter, situation is a bit different. We have preferred, the way we prefer states, we think of them either as, well, if there's either they are thermal states, Gibbs states, or the lowest energy states of some Hamiltonian. And then the question, okay, so we have this kind of states, and the question is, some questions we can ask are how many types are there? Like, are there qualitatively different um, types of entangled states? And also often we want to impose some symmetry, and then see how the answer changes if you impose some symmetry on the, say, Hamiltonians, and therefore on the states. So, okay, that's one of the questions. There are many questions you can ask, but one of the questions is just, is there some qualitative classification of certain types of states? Now, we typically think about qubits living not just like, okay, in quantum information, you consider, like, sometimes specific qubits in sort of abstract qubits, but physical qubits live in some Euclidean space, some dimension D. And I think it is a metric space. And also, well, even in quantum information, people often restrict to gates which are local. If qubits some lives at some point, a gate can involve this qubit and some other qubit only if this other qubit is close enough. So you can only operate at neighboring qubits. That's an assumption someone often makes, and it's actually a pretty realistic assumption. Now, in quantum matter, we also have a sort of locality, because the Hamiltonians, physically realizable Hamiltonians, um, involve interaction between only qubits which are nearby. Now, what exactly it means, it actually matters. If interactions decay very fast, say exponentially with distance between qubits, then it's a very nice situation, and that's we can deal with. In real life, of course, longer range interactions occur. For example, there could be some dipole or even Coulomb interactions, which decay much slower with distance. Any case, we'll try to idealize situations as much as we can, but we should realize there's some gap between what we're really interested in and what we can control. Like, short-range interactions are much easier than long-range interactions. In any case, some sort of locality is important, because only if you impose locality, then the problem of classification becomes non-trivial. It's definitely condensed matter. So anyway, you can imagine, for the purpose of this talk, that qubits just live at points of integer lattice, hypercubic lattice in Euclidean space, even though that's not that important. And you can imagine that maybe there's more than one qubit at a given point. Also an important thing that I already mentioned, it's a good idea to take the limit n goes to infinity. The number of qubits goes to infinity. That makes a problem a bit more interesting mathematically, but also, if you don't take this limit, then any distinction between different types of states is in the end only quantitative. You have all states, strictly speaking, are kind of the same, in some same phase or type. Only in the limit n goes to infinity, the distinctions between different types of entanglement become sharp. So mathematically, it's a very useful thing to take, because otherwise you'll have to always allow for some error, which is difficult. Now, the mathematical difficulty is that if you just take the limit of n goes to infinity, the Hilbert space doesn't have a limit. So there's no limiting Hilbert space in any natural way. So this is was noticed first by John von Neumann. There's a very, very nice article from 1930s called infinite direct product. And I guess terminology at that time was, what he called direct product, we now call tensor product. So he precisely was answering this question: what happens if you take infinite tensor product of Hilbert spaces? Um, and he, explains there that the limit is not really a Hilbert space. And he also proposed in the same paper and studies, a workaround. Instead of looking at Hilbert spaces, we look at the algebra of observables, because that does have a limit. So for a single qubit, the algebra of observables is simply a space of linear maps from this vector Hilbert space to itself. So just algebra of matrices. Or, well, if you have qubits, a bunch of qubits, then you just have a tensor product of this matrix algebras, which is still a matrix algebra. Now, we take the limit and goes to infinity. That actually makes sense because, you see, in a space of linear maps, you have a distinguished element, canonical one, the identity map. Well, in Hilbert space, there's no reason, there's nothing special about any vector in Hilbert space. But here, you can take the limit and get infinite tensor product simply by saying, well, an element of this infinite tensor product has ones everywhere except a finite number of points on the lattice. Okay. And has something else at other points. So that's like algebra of local observables. It's a pretty nice object. It's not a matrix algebra anymore, but kind of infinite matrix algebra. It has a star structure. So we have a map, antilinear map from A to A star, which just extends the usual, dagger on the individual qubits. So it's antilinear, and if you do it twice, you're going to go back to where you are, and it's also anti-homomorphism. So dagger or star, the order of product is reversed. Now, okay, so star algebras are nice, but they're not good enough to do anything interesting physically. Well, okay, that's an exaggeration. In quantum information, you often just stop here, because many of the things you do are purely algebraic. But in quantum statistical mechanics, you can't stop here because you gotta define evolution for observables. And in this context, some sort of infinite n equals to infinity limit of Heisenberg equations of motion. And they involve differentiation, so you cannot define a derivative unless you know, you need to do calculus, unless you know what it means for two elements of the algebra to be close to each other. You cannot even make sense of this. So you need to define some notion of a continuous, at least a continuous and differentiable function with values in this algebra. And when you do it is just define, first of all, notion of a norm. You got to have a notion of a norm. It's a real number, positive, non-negative real number, with the following properties. Well, okay, first of all, if you want to say that if norm is zero, then the element itself is zero. And second should be linearity of this sort and triangle inequality. And some compatibility. Okay, so, and also, of course, completeness. So the most important thing is should be complete. So every Cauchy sequence has a limit. So in the case of algebra local observables, we do have a natural norm because each of the qubit algebras has natural norm, just the matrix usual operator norm. And if you complete, if you take that, then the whole thing also has a norm, and then you take completed, you get something slightly bigger called algebra of quasi-local observables, called AQL, and that you can work with. And there's some compatibility also with the product in this algebra. So, this one, for example, and this one. So the second one, usually people say it means it's a Banach algebra. When you add the first one, that means it's a C-star algebra. So this is a standard setup in quantum statistical mechanics. So observables live in this C-star algebra. Okay, that's pretty trivial. But now we need to actually define these equations of motion. For that, we need to discuss Hamiltonians. So what's a Hamiltonian? Well, a physicist would write Hamiltonian as an infinite sum like this. On each side, you have some observable. This observable is not literally observable of the of the algebra of that qubit or site, whatever. What I mean is that it's an observable which involves several neighboring qubits. but it's localized near that qubit. So each of these terms is Hermitian observable. The problem is that infinite sum is not an element of the algebra. It makes no sense. It's not a convergent sum because these hj's do not go to zero when j is like somewhere far. So it's not an element either of a local or quasi-local algebra, but nevertheless, the expression minus I times commutator of h with any a is well defined. Well, at least for a nice observable, like say local one. That's because if j is far from where a sits, then you might as well just drop them, and then essentially can replace this infinite sum with a finite sum. So mathematically, then you have this operation which to any observable constructs its commutator with h, even though you don't have h as an observable here. And mathematically, this operation is what's called a derivation of the algebra. It's a linear map from the algebra to itself, which satisfies this, like a derivative. Okay, so that's good, but unfortunately, there's a problem. I just argued that quasi-local observables is the right place and the right algebra to work with, but this derivation typically is not defined on the whole algebra of quasi-local observables. So these sums, let's say, they're convergent for nice observables, not for arbitrary quasi-local ones. Okay, so we can restrict to local ones maybe. But the problem is that if you start with, when this h acts on a local observable, okay, so anyway, so even on this one action on local observable gives you another local, maybe quasi-local observable, depends on the Hamiltonian. But the problem is not a nice like a map from local observable to itself, for example. You really need quasi-local ones, but there it's not well defined everywhere. It's defined on some dense subset of quasi-local observables, kind of like unbounded operators in a Hilbert space. Those are defined only in a dense subset. Something which is usually swept under the rug in quantum mechanics, but all operators like momentum, coordinate, they're only densely defined. So, and that's a bit of a problem actually, because when you say discuss, when in classical mechanics, or in quantum mechanics, we usually say, well, it's all very nice algebraic structure. In classical mechanics, observables form a Lie algebra. The bracket given by the Poisson bracket is the Poisson bracket. And that's very nice. That's a natural symmetry algebra of a classical mechanical system. In ordinary quantum mechanics, if you're in finite dimensional Hilbert space, observables form also Lie algebra under the commutator. So you can say, well, this is like an infinitesimal symmetry of a quantum system. You would like to say the same thing for infinite lattice systems, but if you take two derivations, well, if you just say, well, my symmetry, what I mean by symmetry is some unbounded derivation. Well, it's a bit problematic because they're not defined everywhere. They're defined on some dense domain. What if these domains are different for the two derivations? Or maybe if you take the commutator, it's defined, somewhere like not densely or something like that. So, well, it's all technical stuff, and one shouldn't be really worried too much. But in practice, the way to deal with this is to just make sure that all derivations are defined on some common dense domain. We'll discuss later what it is. Anyway, so modulo this, we would like now to use Hamiltonian to define dynamics. That is, see how to implement time translation symmetry. Well, dynamics, so what does it do? Well, it takes an observable at time 0 and maps it to observable at time t. We postulate some properties. First of all, it should commute with the star operation. So, for example, we want Hermitian observable to evolve to a Hermitian one. And we want product, if you take product and then evolve, or, first of all, take product, it's the same thing. So it's this time translation symmetry, in other words, acts by homomorphisms, actually star homomorphisms of the algebra. And well, that's actually not true just about symmetry under time translations. You can consider any symmetry, and it's natural to postulate that whenever some symmetry, it should preserve algebraic relations between elements, so it should be star actually automorphism. Should be probably, if it's a symmetry, it should also be an inverse. So you should have such maps should be have all invertible. So in ordinary quantum mechanics, we have such things. When you look at operators, you have unitary transformations on Hilbert space, which you can use to map operators. Here we don't have Hilbert space, at least not yet. We just map operators, but then you can think of these star automorphisms as C-star algebraic analogs of unitary transformations. Okay, so how do we relate this notion of a time translation symmetry evolution with the Hamiltonian? Or more generally, how do we relate? Okay, how do you think about continuous symmetries in terms of generators, as physicists would like to? Well, actually, the same way as in quantum mechanics. So suppose you have, say, one parameter group of symmetries, meaning that you have transformation which depends on the parameter t, which is a real number, and if you compose transformations, then it's the same as doing a single transformation with the added parameters. Then you can just take derivative with respect to parameter and set t to 0. And that gives you a linear map from your algebra to itself. So delta is called the generator of symmetry. And it's not easy, it's not very easy to check from this one. The generator is also derivation. So from one parameter group, you can define its generator, which is automatically derivation. So for example, we expect the time translational symmetry to give rise to the Hamiltonian as a derivation. If you have some other symmetry like electromagnetic U1 symmetry, then this also has a generator, which is also some derivation, which is electric charge. So it's a bit funny here because the automorphism is supposed to act on arbitrary observable, but the generators are not defined everywhere, only on some dense subspace. Well, of course, what happens is that this derivative, it's not defined for all A's. It exists for some A's, it doesn't exist for other A's. One can show that the derivative also exists for a dense subspace, and that's why all these derivations we get in this way are densely defined. In any case, notional derivation is kind of way too general. And the one we really care about, they have fairly explicit form, like this one. Take infinite sums over sites, and then on each site you have some sort of density of a derivation, and then you just take commutators and then sum up over all sites. So if we're like constructing charge generator, then these QIs are just charges of individual sites. If you have a Hamiltonian, then these Q's instead of these Q's become like energy of particular size, kind of energy density. So yeah, so this is how we expect generators to be. Of course, in real life, we don't actually start with the symmetry and then derive generator. We typically try to work our way back. We start with the generator, like Hamiltonian, and then try to exponentiate it to get the time evolution. What does it mean? Well, we're supposed to solve this equation. So for the evolution operator. So we know the Hamiltonian, so we can there's a derivation, so we can write it in either more physics notation like this, or more math notation. Either way, we're supposed to solve this differential equation, and this is a sort of C-star algebraic analog of Heisenberg equations of motion. Sometimes people call this thing the Liouvillean, this commutator with H. Well, formally, of course, not very difficult to solve this. We just write, like as I say, exponentiate this commutator operation. Right? If you denote the commutator with H, add H, then you just need to write this exponential series. But the question is like, well, can you actually, does it make sense? This infinite sum, does it actually converge? If you start with a nice observable at least. And well, this formal stuff, you can also like formally do it in quantum field theory. But in quantum field theory, we typically discover that these expressions are formal, and we're not sure how to make sense of them. The nice thing about lattice systems is that actually you can prove that the series converges. Or alternatively, you can just directly maybe solve this equation, this Heisenberg equation of motion, or quantum Liouville equation. Okay, maybe I shouldn't call it Liouvillean. So when people talk about Liouville equation, I mean the equation quantum Liouville, they mean evolution equation for um, for a density matrix. So here I am doing not density matrix, but operator. Evolution for operators, for observables. Actually, I shouldn't say operators, for observables, because we don't have Hilbert space. So these little a's are not operators on a Hilbert space. Okay, so what do I mean by nice observable? So actually, like when I say like you start with a local observable, for example, which is a very nice thing, and then you evolve it and you hope that it's still fairly nice. What do I mean by nice? Okay. So a natural way to measure how nice a particular observable is this. It's A is quasi-local. Um, you can ask, okay, how well can we approximate it by a local observable? Well, here's the observable A of t, say. We don't know much about them. Suppose it's quasi-local. We look at the error we make if we decide to approximate it by some B, which is a local observable living in a ball of size R. So BJR is a ball of size R with center at J. Okay. So here's so that gives you some number, which depends, of course, on the side J, on the R, and on observable you're trying to approximate. So any quasi-local observable, by definition, is a limit of some sequence of local observables. So if A of t, as a result, if A of quasi-local, then for large enough R, you can approximate the error with arbitrarily good accuracy. So this function will decay to zero as R goes to infinity. But for quasi-local observables, that's pretty much it. We cannot really say anything more about this function. Okay, it decays to zero, goes to zero as R goes to infinity, but that's about it. We don't know how fast. And that's not enough to say anything, to do anything useful with this function. But you can say that, well, if you do know that, some special classes of observables, for example, decay exponentially, for each function decays exponentially, or maybe some negative power of R. We could say that it's almost local in the sense that we have pretty good control over how well it's approximated by local ones. Okay, so finally, there's this meta theorem. Finally, we get to this Lieb-Robinson bound. As a meta theorem, it's really a meta theorem which says that if your Hamiltonian involves only short-range interactions, then ace of t is almost local. So, roughly, the size of ace of t grows linearly with t. Okay, strictly speaking, it's true for A, which is doesn't have like power-like interactions. But a version of this theorem also makes sense for power-like interactions if they decay if the power is large enough. Except there, of course, the size of AT does not grow linearly with time. So the fact that size grows linearly with time up to some corrections. Well, I mean, there's some this is a place where the most of A of t is localized. It's some disk whose size grows, ball whose size grows linearly with t, and then outside this ball, A of t has some parts, but it's very, very small. So this, the size of the velocity with which this ball grows is called Lieb-Robinson velocity, because it was, this phenomenon was first observed by Lieb and Robinson in 1972. And specific formula for this function, for this error as a function of R, called Lieb-Robinson bound. Sometimes you can see it, actually in most papers you can see it in a bit different way. Instead of saying that it's a best approximation to A of t by local observables, you can say, well, it's instead you just ask how big is the commutator between A of t and some observable outside the ball of radius R. But it's literally the same thing. It's one can show that the norm of the commutator for observables outside of the ball radius R is the same as the error with which you can approximate your observable by living on a ball itself. So, okay. Anyway, here's a picture I already alluded to. So we have some, here's a vertical axis is time, horizontal is distance. We start with some local observable right here. As time evolves, if you look at time slice, the observable, sort of its size gets bigger and bigger. But outside this sort of light cone, it's not zero, but it's very small, typically exponentially small, as this sort of picture shows. Yeah, so there's no exact light cone on the lattice, but there's an approximate one. And velocity v is called the Lieb-Robinson velocity. It depends on the Hamiltonian. But this property is important, but also not just special to lattice systems. In the following sense that this is some statement about evolution which makes no reference to the state. Now, if you look at some systems in the continuum, like say, I don't know, this particle in the continuum, it's pretty clear this cannot be a theorem like that. For example, if you look at a bunch of fermions in a continuum with some potential interaction, how fast do signals propagate in such a system? Like suppose all I know is the Hamiltonian. Can I say that? And the answer is no, not really, uh, because the state actually also matters. So if I ask, if you choose a density of fermions, which is property of a state, not the Hamiltonian, I can get, if the density is large, then velocity is also going to get larger. So how do we see that? Well, because the relevant velocity for, say, weakly interacting fermions is definitely the Fermi velocity, which is determined by the radius of the Fermi sphere. But that depends on the density of fermions. So for a very large Fermi surface, you're going to have a very high Fermi velocity. So you cannot tell how fast signal propagates without fixing the state, actually, not just the Hamiltonian. But on the lattice, you don't need to know the state. You can put an upper bound on velocity simply just knowing the Hamiltonian. Of course, if you're on the lattice, you cannot have arbitrarily large Fermi sphere because there's only, can only put at most one fermion of a particular quantum number on your site. So this discovery of Lieb-Robinson was completely not noticed for decades, for many decades, like 30 years. And that suddenly became very, very important. And the reason it became important is because, it's really powerful if one assumes also energy gap. So what's that? Well, first of all, let's discuss states. So far we have analogs of operators. What about states? Well, a state in this system algebraic framework is simply a positive linear function on the algebra, such that first it's like expectation value. So expectation value of one, of course, is one, but on other elements, it's whatever. There's only one constraint, that expectation value of positive quantity, meaning like things like A star A, is by definition positive, must be non-negative. That's all. I could ask, what about continuity? Shouldn't it be called a continuous function on the algebra observables? Miraculously, it turns out that continuity is automatic. Any positive linear function on the C-star algebra is continuous. Now, for finite system, all such states, finite, I mean like finite number of qubits. All such states have a very simple form, just trace of some density matrix times A. Okay, so but in this statement doesn't even make any sense for a system of qubits because we don't have a Hilbert space around. So there's no notion of a trace. By the way, this statement actually not even true for infinite dimensional Hilbert space. If you ask, in that case, instead of algebra of quasi-local observables, you have bounded operators on a Hilbert space. You can ask, okay, what is a positive linear function on the C-star algebra of bounded operators in the Hilbert space? And okay, clearly, density matrix, that is a trace class positive operator, gives rise to such a thing. Here it is. But maybe there are other weirder states which don't have this form. Now it's like for a physicist, it's like a crazy question. Of course, like what are they talking about? It must be some theorem which says that these are one and the same thing. Turns out that's actually not true. In fact, they have a pure state which not on this form. So I remember at some point I read Feynman's one of Feynman's books, maybe Surely You're Joking, and he was saying there that when he was a uh, graduate student, he liked to annoy mathematicians by saying that he can guess whether some mathematical fact is true or false without any proof, just by thinking, just by intuition. So like basically math is useless because anyway we can tell what's true or not without math. I wonder what Feynman would have said about that, because if you ask any physicist who's not like an expert on this statistical mechanics, whether it's on functional analysis, whether it's true that any positive function, positive linear function, comes from a density matrix. In the case of a Hilbert space, they would say, of course, but it's wrong. But okay, so um, anyway, so I'm gonna dwell on this because we don't have Hilbert space anyway. So next we want to define a ground state. So now what's a ground state? A ground state is a state with this property. Well, in Hilbert space formalism, you say, well, ground state is the one which has the lowest energy. It's an eigenvector of the Hamiltonian with the lowest eigenvalue. In sister algebraic formalism, this is the right analog of that. Okay, so well, how do I know that? Well, like it seems like a very unintuitive condition. Well, so here at this point, I need to explain, the relation between the sister algebraic stuff and the usual formalism with Hilbert space. So the point is this: given a state, you can construct finally a Hilbert space. We call it curly H, calligraphic H, and the representation. There is a map from your algebra to bounded operators actually on Hilbert space. So nothing unbounded here. By representation, I mean just simply the usual thing. So you have a map of each operator, each observable maps to an operator, and all algebraic relations are preserved. So say pi of AB is equal to pi of A plus times pi of B. And same for the star. So pi of A star is the same as the dagger of pi of A. Okay, we have to have that, have a representation, have a vector, special vector called the vacuum vector, called V, and has the following property. You can compute expectation value of any observable by taking the corresponding operator and taking the average in the usual quantum mechanical sense. So yeah, so this Hilbert space and its representation, a vector obtained by some construction called the Gelfand-Naimark cycle construction, which I'm not going to describe here. The important thing is this, that if you start with an evolution, which has some generator called delta H, and this evolution preserves the state, that is, if the average doesn't depend on the time, then you can also represent evolution using Hilbert space. Namely, there is some unbounded self-adjoint operator on the Hilbert space, which first of all annihilates your vacuum, and second, it represents evolution in the following sense. If you start with, if you ask, if suppose you know how to represent observable A using pi of A, well, then A of t is represented simply by the usual evolution, like by conjugating with evolution operator in the usual sense. Okay. So H hat is an operator, is an honest operator, well, unbounded one, which represents this evolution, generates evolution. And now I claim is that this strange condition, which I wrote before on a previous slide, this one, can be is equivalent to saying that the spectrum of the this operator is non-negative. In particular, so this energy is always when a state is at least zero. And in particular, the vacuum vector has zero energy, so it is the state of lowest energy, namely zero. That sort of explains why this strange definition is made. So that does reflect actually the intuition. Okay, so let's say, okay, why don't I? Okay, that's great. Now I have this construction, but I don't want to work with it too much because it depends on the choice of a state, and I want to compare different states. So I don't want to work in Hilbert space because I just want to be able to say, well, these states are different, these states in the same phase, same type, and if I stick with a particular representation, I cannot really discuss other states. Okay. Anyway, so I was just trying to explain why Lieb-Robinson bounds are useful. So okay, so as I said, the important thing is to have a gapped state. So ground state is simply a state of lowest energy. It's basically the same as Gibbs state at at zero temperature. But we're interested in special ones, namely the ones which have an energy gap, which is sort of rigid or incompressible. Again, there's a systology break, a way to write it, and it's a strengthening of the previous inequality. So the expression on the right-hand side is non-negative. So instead of saying that this left-hand side is simply non-negative, you say it's actually bigger than this thing here. And if you translate it back into the Hilbert space language, all it says is that in this Hilbert space, not only, okay, so in the Hilbert space, definitely the vacuum has a zero energy, but this extra condition, more strong condition, says that all other states have energy at least delta. Okay, so that's gap condition. Now, okay, so of course in nature there are states which are both ground state can be both gapped and not gapped. Say superconductors and systems with quantum Hall effect are gapped, while superfluids, crystals, ferroliquids are gapless. Well, from this list of examples, you can see that gap states are somewhat exotic. Most states are gapless. But since the 80s, when quantum Hall states were discovered, it was realized that gap states are very, very interesting and weird. So so we wanted to study them, and these are the states related to topological field theory. And it is this rigidity of the states expressed by is that what leads one to think that they might be described by topological field theory. And my goal is to explain in what sense, how do we see that something is rigid about them? And this comes from a combination of two things. First of all, they have energy gap, and second, this Lieb-Robinson bounds. Okay. So first fact about this gapped ground states and where this whole excitement about Lieb-Robinson bound started is the result by Hastings, and also for the work by Hastings and Coma. So it's the following. So suppose you have a state, a gapped ground state of a Hamiltonian, which has this form. It has it's some local term, and each term is exponentially well localized in the sense I described, namely that if you look at the approximation error, well, it's decays exponentially with distance. So the claim is that then correlation functions for the state always decay exponentially. That is, you can upper bound the correlator in a way which, by some expression which actually decays exponentially with the distance between supports of the two local observables. Also, the generalization, same in the paper by Hastings and Coma, if your terms in this Hamiltonian only power like localized, well, for power greater than dimensional space, then the correlators still decay, but now only like a power. Well, they're guaranteed to decay at least as a power. Okay, some other power, not the same as n. So that's already kind of, in some sense, means indication of rigidity, because it means that um, roughly speaking, correlate is tells you what happened, the influence of one patch of material on another patch. If the correlator decays, then that means that presumably they don't really talk to each other. Perturbing in one place doesn't do anything to the other place. I'm not going to try to prove that here. It's pretty complicated proof. They're very ingenious. But just say the Lieb-Robinson bounds are really crucial here. So this correlation decay is important. But instead, I'm going to outline another proof of another fact. Again, using Lieb-Robinson bounds. So which has very, very, very many applications. uh, to topological phases. Let me start with one version of, the one version of this result. There are several types, similar ones. Suppose you have a Hamiltonian, which is some local terms. And you say that from definition, a ground state is frustration-free if it is an eigenstate of each term in the Hamiltonian, not just the whole Hamiltonian. And I say that kind of Hilbert space approach, but this is a sister algebraic way of saying this. One says that none of these HJs excites the state. That's expressed like this: expectation of a commutator with any observable is 0. Remarkably, it turns out that if you have a gapped ground state, then it's always frustration-free. What does it mean? Well, the point is this: when I write the Hamiltonian with some of local terms, there are actually many different ways to write the same Hamiltonian with some of local terms. That's pretty clear. And Kitaev's theorem says that actually there's always a way to split your total Hamiltonian into local terms, call them H tildes, so that each H tilde does not excite your ground state. How is it proved? Okay, I'll explain later, like from a different viewpoint, like this ambiguity. It seems a bit weird. Okay, so how much ambiguity actually is there? So we have this original, say, presentation of Hamiltonian, then you try to look for another one. It would be nice to understand how what is the ambiguity. But I'll discuss it later. But let me just explain how this theorem is proved. So suppose you have a finite quantum system as a warm-up. So later we're gonna do the real thing, but just look finite quantum systems with energy eigenstates, call them n. And so that there's a gap. So En minus E0 is greater than delta for n greater than 0. This is a non-degenerate ground state. You can say that energy is 0, E0 maybe even 0, but okay, I don't gonna say that. Just energy difference is at least delta between ground state and excited states. And consider it's a map from observables to observables, so from operators to operators. In this case, just operators because it's a finite system. Map goes like this. Suppose I have a theory observable B. I assign a new observable called B tilde, whose expansion in the energy base is epsilon like this. You start with the original expansion, this matrix element, and then I multiply it by some number, which is a function of, this number depends only on the difference of energies, En and Em. Namely, so this function of energy is even, that is, exchange energy to minus energy doesn't change. If the energy difference vanishes, then it's 1. And if it's great, and if the energy difference is greater than delta, then it's 0. And that's it. I don't impose anything else for now. Okay, so just yeah, so what does it do? Well, this transformation. Well, if B is diagonal in the energy basis, then this B and M is non-vanishing only, for En equals to Em. So then, of course, this transformation does nothing. So B tilde is equal to B because, W tilde of 0 is 1. Okay. Also, it's easy to see that the average in any state is the same, regardless of what B was. So that does change the energy average and energy eigenstates. Again, because the W tilde of 0 is 1. And finally, if you look at the matrix element with a vacuum and any other state, you're going to get 0 for B tilde. That's again because W tilde vanishes for sufficiently large energy difference, but we assumed gapped. So any state which is not ground state separated from it by gap, so it just kills it. Yeah, so we basically modify your observable in such a way that your operator in such a way that you kill all matrix elements between ground state and the vacuum, ground state and the excited states. Okay, in particular, you can apply it to the Hamiltonian itself. Well, for a finite system, it is an operator. So let's see what happens. Um, so capital H tilde, well, H is diagonal, right, in its own basis. So of course, by first property, it's the same as capital H tilde, as H. Nothing changes there. But it's a linear transformation, so individual energy densities at little h's do change. Okay? So this operation allows you to rewrite the same Hamiltonian, your original Hamiltonian, the sum of terms, such that each vacuum is an eigenstate of this local term. Okay, just as I claimed. So, and that's true for any choice of this function, W tilde. Okay, so did we just theorem? Well, and I didn't even use Lieb-Robinson bounds. Well, the answer is no, we cheated, but we can like fix that. So first, if you want to do infinite systems, we can rewrite B tilde, its transformation from B to B tilde in a sort of terms which make sense in infinite volume. So easy exercise, that's how you do it. It's some integral transform. You start with the B, you evolve it for time t, that's your evolution operator, multiply by some function, and then integrate over the whole all times. And if your W of t is simply Fourier transform with this W tilde, then you can check that it's exactly the same transformation I wrote in the previous slide. Just go to energy basis. And now we have this transformation, which makes perfect sense, even if makes sense in even the algebraic case. How do I know it makes sense? Well, because evolution operator is well defined, and if I choose W of t to decay rapidly with t, for example, faster than the power of t, then of course the integral is going to converge, right? No issue with convergence. Of course, for this to make sense, I need to learn how to need to have a theory of integration of functions with values in a sister algebra. But we made sure that we have a good calculus, such things. Okay, so we have this well-defined transformation, and then what do we see? Well, if t is large, um, then okay. So if t is small, this thing is approximately local. But if t is large, then, well, contribution of that is negligible. Again, if t is large, then this observable is not very local because it's spread to a very large radius. But W of t is small there, so that's got a negligible correction. As a result, this whole thing is almost local. In fact, its tail sort of, it's this error function for it, decays faster than the power, or even exponentially. So this transformation then applied to every this energy density term will give an almost local observable. And you can show in exactly the same way as before that when I apply to the whole Hamiltonian, you just get back the original Hamiltonian. So this argument actually works. Okay. Okay, that might not be very impressive because the question itself kind of strange. Why would I want to have this frustration-free property? But here's something which is maybe more recognizable, proved in a similar way. Suppose you have a ground state of now U1 invariant Hamiltonian, and suppose it's also gapped. Then I claim that state is actually U1 invariant itself. So asking questions is, yeah, can it be, in other words, so can it be that the ground state of a Hamiltonian, of U1 invariant Hamiltonian, is not U1 invariant? We know that in general that can't happen. It's called spontaneous symmetry breaking. But I'm saying that if the ground state is gapped, then that cannot happen. Then the state is definitely U1 invariant. So that's basically the same as Goldstone theorem, or some weak form of Goldstone theorem. Goldstone theorem says that, well, usually people say it this way: if you have spontaneous symmetry breaking, then the state must be gapless. There must be gapless excitations, Goldstone bosons. But I'm here kind of saying the equivalent statement that if the state is gapped, that cannot break U1 symmetry. And usually, if you look at the textbooks, this is proved on some additional assumptions, at least translational symmetry, or in QFT under Lorentz symmetry. But actually, this weak statement doesn't need any of that. Let me explain how it's proved. So I'm not going to go into so much detail now. Suppose I have a charge. It's a derivation. It's some local terms. And as with Hamiltonian, can do some like similar things and show not the same, it's not similar arguments can show that you can split this big Q into little q's, Q tildes. So the sum is still capital Q, but now each of these observables don't not excite the ground state. That can be done provided the state is gapped. And the proof uses again Lieb-Robinson bounds. By the way, maybe at this point I should at this point it's good to actually ask ourselves, so like, how big is this ambiguity we're talking about? Where did this come from? Well, first, it's easy to think about continuum field theory. In continuum field theory, you write integrals instead of sums. So the Hamiltonian is an integral of Hamiltonian density, and charge integral of charge density. And ambiguity here is clear. You can just add to say energy density to any divergence of any vector, and same for charge density, and nothing changes as far as the only boundary terms appear, but they don't matter if you take commutators with things. They drop out. On the lattice, the similar thing. If you replace your Hamiltonian density, energy density, with this expression, where A, J, K is just any function of 2 points on the lattice, which skew symmetric and kind of decays for large J minus K, that's still a valid charge density or energy density. But you can easily check that the corresponding derivation actually is the same. That's basically, naively, you could just say, well, it's obvious. If you let's sum over this overall J's. Well, if you sum over all J's here, then, this term just drops out, right? Because of skew symmetry. It's a bit sloppy because, the infinite sums don't make much sense. But if you do it inside the commutator with some local observable, that does make sense, and, the argument works. Okay. So when this Q tildes, if I'm finding here, since they sum up to the same charge, they must differ from Q's by this kind of expression, by this sum over some quantity which is Q-symmetric into indices. So actually, one can write down. I'm saying that there's a theorem which actually says that these ambiguities, which I wrote down, are actually the only ambiguities in splitting your derivation into local terms. So in particular, these Q tildes must be different from Q simply by this kind of expression. And this Kitaev type argument allows you to write down a formula for this, K, capital K. Again, in terms of some integral over time. Well, this capital W is not this old W. It's sort of an integral of W, little w. Okay. And now I'm ready to prove this weak Goldstone theorem. Well, suppose you have a U1 invariant state. Oh, so U1 you want to prove that state is U1 invariant, and it's the same thing as proving that expectation value of the commutator of Q with any observable is 0. So that Q doesn't excite the ground state, omega. How do we prove that? Well, A, it's a local observable. It lives somewhere. So let's choose a large ball containing the support of this observable and evaluate, expectation value of commutator of this regularized charge with A. And then we're going to take limit r goes to infinity. And then we're going to recover what we want. So, okay, let's look at this. So what is this QR? It's a sum of local charges. But now we can rewrite in terms of these Q tildes. So recalling the relation between Q's and Q tildes, we can write it this way. So sum now over J's inside this ball, and here we sum over J's inside the ball, while by the sum over K's is over all little K's, over all the whole lattice. Okay, now we're supposed to take commutator of this thing with A and take average. And the first term clearly doesn't contribute, right? Because by assumption, all these Q tilde J's don't excite the ground this state omega. So each of these terms, when you commute it with A, has 0 expectation value. So we only have the second term to worry about. But the second term is concentrated near the boundary of the ball. because when you sum, when both J and K are inside the ball, these terms just cancel out because this capital K is Q-symmetric. So you only have terms where J is inside the ball, but little k is outside the ball. But this guy, the gadget capital K, decays when J and K are far from each other. So only when J and K are close to each other, you get some appreciable contribution. And that only happens when they're on the boundary of the ball. Okay. And then now we take, so this combinator result is going to be very small because only contribution comes from the surface of the ball, and the surface is very far from where the observable is, which is deep inside the ball. And you take R to be very, very large, the expectation value becomes smaller and smaller. But that's precisely the limit when you are supposed to recover this expectation value of interest. So in this limit, you prove that the expectation value just vanishes. Okay. And so all this comes from the existence of this improved charge densities, which in itself comes from the fact that they're Lieb-Robinson bounds. So last application I'd like to discuss is to actually construct some invariant, topological invariant of a state. Okay, I mean not last application, like last sort of solid clear application. So I wanted to construct a numerical invariant of a U1 invariant gapped state. And when I say gapped, I mean that there is some Hamiltonian for which it is a ground state, but I don't really care what it is. All I want to know that this Hamiltonian exists. And now this construction is going to be special to two-dimensional lattice. So first of all, I choose this improved charge densities. And I didn't say it, but you can also choose it with additional property that they all commute with the total charge. I mean, the usual charge density, of course, commutes with the total charge. Like each charge density is itself U1 invariant. But it's same true about these Q tildes. Okay, there's a lot of ambiguities how I choose them, but still. I'm just saying, well, if choose in some way and then just average over U1, U1 symmetry, then the thing's going to be one invariant, and then they're going to commute with total Q. So that's the usual averaging trick. Okay, now let's do the following. Let's divide the plane into 3 cones. And the boundaries between these cones can be actually very wiggly. I don't care very much. They can go like this. They might actually even overlap. That doesn't matter. Actually, no, let's not do that. Let's just say, yeah, so I just let sharp boundaries, but they can be like wiggly. And let me define Q tilde, capital Q tilde, I, for I equals 1, 2, or 3, just to sum of all these improved charge densities over that region. Of course, if I sum over all sides, I'm going to get the original capital Q. Okay, now let's think about this. Let's look at the commutator of charges in regions 1 and 2. So where does it live? It's a sum of local terms, but which local terms? Well, these Q tildes are almost local. That is the well localized near the site J. So when I take commutator, things which live out there and out there, they essentially commute. So this J12 can be really concentrated near the boundary between regions 1 and 2. So near this line, not exactly, but the tails are like it's a sum of local observables too. It's a derivation which is sum of local observables formally. But these local observables, the farther you get from this region, the smaller they are. Very, very fast also. But in fact, more is true. It's actually concentrated near the origin, near the place where all 3 cones intersect. So why is that? Well, recall that, Q tilde 1 is simply, capital Q minus the other Q tildes, okay? But Q tilde 2 comes with itself, as well as with Q. So we get this. But that's clearly concentrated near the boundary between 2 and 3 by the same argument. So something which is concentrated near this line and this line must be concentrated near the origin. So this derivation is literally concentrated near the origin, which means it's a commutator with something which is just local observable. There's no other way to achieve that. And local observables have expectation values. Okay, the way I set things up here, this is anti-Hermitian local observable, so its average is purely imaginary. So let's multiply by minus I to get something real. So we get some real number out of this expectation value of this local observable. And here, let me just make a list of things which are true about this number. First of all, this number turns out to be the zero temperature Hall conductance of the system. Second, well, for this to make sense, of course, before you prove that, you need to make sure that the result is independent of the choice of these cones. So you can do it yourself. It doesn't require much, but I'm going to do it here. It's a nice exercises, but kind of amazing in a sense. Like this number, so much ambiguity in how you define it, but you change the cones by quite a lot and nothing changes, like literally nothing. And also, in the end, turns out to be independent of how one chooses this improved charges. A lot of ambiguity there, even if, with all the constraints we put on them, in many ways to get such things, and not that doesn't matter either. So this number is topological invariant of one invariant gapped state. And by the way, I never ever use the Hamiltonian here. I just knew that Hamiltonian exists, but I don't care what it is. It's an invariant of a sort of a pattern of entanglement of a state, and the only other thing you need to know about the state is U1 invariant. But the Hamiltonian is not an invariant of a Hamiltonian. Okay. So that illustrates how to, Lieb-Robinson bounds leads to actual numerical invariance. And literally the last thing I want to say is talk about gapped phases of matter. What's a phase of matter? Well, we believe that gapped phases of matter perhaps are related to topological field theory, at least in some special, under maybe some additional conditions. But actually, what's a gapped phase of matter? Well, it's some equivalence relation, it's some equivalence class of states, of gapped states. And well, what sort of equivalence relation? Well, minimal requirement is that if we define some topological invariant of a state, kind of like this Hall conductance, it better be the same for all states in the same phase. So here is a first attempt at defining such a relation. So suppose we have a time-dependent Hamiltonian. Lieb-Robinson bounds can be generalized to this case, and they imply that you can actually solve can find the evolution operator for time-dependent Hamiltonian as well, and that gives you some automorphism of the algebra, and if you compose this automorphism with a state, you get another state, right? Because it's still positive and still linear. And so my first attempt to define equivalence relation say that two states are equivalent or in the same phase if you can sort of evolve for some time, finite time, and then compose the state, and then get the other state. Well, it's easy to check this equivalence relation, so it's symmetric, reflexive, and transitive, but not quite right still. First of all, we need maybe some G covariant version. There's some symmetry, G, which preserves both states. We want to classify states with given symmetry. Then probably we want to we demand this Hamiltonian, which we used to evolve to commute with all symmetries, so that the evolution operator also commutes with all symmetries. Okay, but also even if we forget about symmetry, we would like to compare states systems on different lattices. So we're gonna declare well, how to do that? Well, this what I explained, just to compare states on the same lattice for some lattice system. Well, we declared that tensoring or stacking with the trivial states, unentangled states of some additional lattice systems actually doesn't change the equivalence class. It's very natural. If you unentangled states are very boring, so like it should be regarded as trivial. And here's a better than a definition. maybe not still final, but anyway, we say that two states of two different now algebras are in the same phase if they can be related by this kind of time-dependent evolution after you stack both of them with some auxiliary systems in trivial states. So that is you, you, you say the equivalent, we can find some other algebras, quasi-local algebras, and some other trivial states, omega 1 prime and omega 2 prime, so that if after you stack these things, then you can find a time-dependent Hamiltonian which relates them. And that seems like a pretty good definition from a physical viewpoint, but I'm not convinced or 100% sure that it's the right one, but it's certainly a step in the right direction to make it mathematically precise, what I mean by gapped phase. So let me finish by um, still open problems. First of all, I explained how to define Hall conductance, which is a topological invariant of a system with a symmetry. We still don't know invariance of gapped ground states without any symmetries. That will just measure purely pattern of entanglement. So the question is, other like numerical invariants, we just measure pattern of entanglement or it's just some gapped state. I don't know any examples. For some, but we believe they're there. Topological field theory suggests they should be there, especially in low dimensions. Now, in general, of course, we would like to classify these phases. In one dimension, actually, it has been done using essentially basically the same definition I just explained. And the answer is, well, without any symmetry, just trivial classification. Two-dimensional case is open, though, even though, their TQFT makes very precise prediction, but we don't know how to prove it. Moreover, well, or in two dimensions, you probably expect, phases just to be labeled by quantum field theory. It would be very nice to prove that. And from physical viewpoint, this theory I explained, it's all very nice, but physicists would ask, okay, why is it even relevant? Because in all physical systems, like say quantum Hall systems, you have Coulomb interactions, which are long range. All of this breaks down once you include such interactions. So that's a very important physical question, which I don't know how to address. Okay, and I'll stop here.